Hi everyone, today I'm going to present a tutorial on CFD simulation of a buoy in head waves using DFBI and Overset mesh techniques. The problem is defined here. Here we have the characteristics of both wave and buoy. To fulfill the main purpose of this tutorial, we're going to use the DFBI technique, which allows us to model the motions of a rigid body due to the applied forces and moments, together with the Overset mesh technique as shown here. The overset mesh, which contains the rigid body, is superimposed over a background mesh which is normally stationary, as shown in this figure, right? Background and overset mesh region, where the rotational movement of a body is modeled here. Okay. One important advantage of the overset mesh technique is that it allows the simulation of complex motions. As shown in this figure, depending on the position of the cells within the computational domain, they can be used as active, passive, and acceptor cells. Active cells are the cells that actually are used for the simulation, and the governing fluid flow equations are solved within them. Passive cells are those that no equations are solved within them. Acceptor cells are those that are located between active and inactive cells and facilitate interpolation of the information between the overset and background meshes. The simulation setup is performed in the following steps. The first is a definition of the computational domain, then the definition of the regions and boundary types. This is followed by the mesh generation, then the definition of physics and boundary conditions, and then we have the definition of monitors, solver settings, and stopping criteria, and at the end we have the post-processing. Now let's dive into each of these steps. So first, the definition of the computational domain. Start up STAR-CCM Plus in a manner that is appropriate to your working environment and create a new simulation from here. Choose the number of cores here in such a manner that it's compatible with your PC. I'm going to choose 8. Go ahead and click OK. From here you can save your simulation. Okay. I'm going to call it buoy motions. For this tutorial, all the geometries and domains are created within the STAR-CCM Plus. Totally, we need to create the background and overset domains together with the buoy geometry. Let's first create the background domain. So go ahead and expand geometry from here. Right click on parts. From new shape part, select block. For corner 1, put -10, 0, again -10 for the coordinates, and for corner 2, put 20, 10, and 10 for the coordinates. Go ahead and click on OK. So in order to see the block geometry, right click on scenes, okay, then new scene, and select geometry. You can see here the block that we just created. Okay, right click on block and select duplicate from here. Go ahead and rename the block 2 to background. To define boundary conditions on each background surface, we need to split background surface, expand background surfaces, and here right click on block surface and choose split by patch. Select 28 and go ahead and rename it to symmetry. Click on create here, select 32, and go ahead and rename it to outlet. Click on create. Now go ahead and close the dialog. Go ahead and rename the block surface to inlet. Save the simulation from here. So now to create the overset domain where the buoy is located, go ahead and right click on block and then duplicate. Let's close this one, block, and duplicate. Okay, so now go ahead and rename the block 2 to initial overset. Now let's modify the dimensions of the initial overset domain. Okay, in the properties windows that we can see here, we click on initial overset, and the properties window here put 3 0 -3. Okay, for the start coordinates, while for the end coordinates put 7 2 3. Now to create the buoy geometry, right click on parts, new shape part, and select cylinder. Okay, for the start coordinate put here 5 0 and -2. Okay, and for the end coordinate put 5 0 and 2. Okay, put 0.5 for the radius. Okay, click on create and then close. We have created the cylinder here also. So now right click on cylinder and rename it to buoy. Okay, under buoy surfaces, right click on cylinder surface and rename it to buoy also. Now we need to subtract the buoy from the overset domains, so go ahead and multi-select both the buoy and initial overset. Okay, and right click on one of them and select boolean. From here you can choose the subtract, set the target part to initial overset, go ahead and click on OK. Okay, go ahead and rename the subtract to overset here. Under the overset surfaces, right click on block surfaces and split by patch. We need to split the surfaces of the overset region also, okay? Select 132 surface and go ahead and rename it to symmetry. Click on create and then close. Now go ahead and rename the block surfaces to boundaries. Go ahead and save the simulation. To view these new parts, right click in the empty space of the graphics window and select hide all parts. Select the background node and drag and drop it into the graphic window. Part displayers, put to geometry, and we can do the same for the overset region also. Okay, if we make everything clear from here, we can see that the buoy is in fact fully contained in the overset domain. Go ahead and save the simulation. So now that we created the parts, we go ahead and right click on them on background and click on assign parts to regions here. Set it to create a region for each part, create a boundary for each part surface, and here do not create interfaces from contacts. Go ahead and click on apply. We need to do the same for the overset region, and go ahead and click apply and close the dialog. We can visualize the regions we just created here under regions, right? We have two regions, background and overset. Okay, so now let's define the boundary types. Expand regions, then background, boundaries, select inlet and set the boundary type here to velocity inlet. The outlet, set the type to pressure outlet here, and symmetry, let's put the type to symmetry plane. Now expand the overset boundaries, select boundaries and set the type to overset mesh. Now select symmetry and set the type to symmetry plane. Go ahead and save the simulation. An important point here is that we have to use the same boundary type for boundaries of both the background and overset domains that are coplanar. In this case, we have the symmetry boundaries in both the background and overset domains that are coplanar. To create mesh, right click on the continua here, select new, then mesh continuum. We're going to assign mesh 1 here to the background region. Okay, right click on models and select meshing models. We're going to use the surface remesher, trimmer, and also the extruder. Go ahead and close the dialog. The extruder option will be used for the outlet boundary. The main reason to use extruder here is to dampen the waves close to the outlet boundary by producing orthogonal extruded cells where the size of the cells in the wave propagation direction is increased exponentially. Click on now under models, click on trimmer and check the do mesh alignment. Okay, now under reference values, leave the base size as its default value. Okay, set the maximum cell size here to 100. Under surface size, set both the relative minimum size and the relative target size to 2.5. Under template growth rate, set both the default growth rate and the boundary growth rate to slow. Okay, go ahead and save the simulation. Now let's set the mesh size values on the domain boundaries. So go ahead and expand the regions under background. Expand boundaries. Okay. Multi-select inlet, outlet, and symmetry, and right click on one of them, select edit, expand mesh conditions. Under custom surface size, check custom surface size. Okay, so under mesh values, put 100 for both relative minimum size and relative target size. Go ahead and close the dialog. In this tutorial, as we are using the VOF approach to resolve the position and the shape of the free surface, it is necessary to apply proper local mesh refinement at the free surface. In this regard, as a rule of thumb, as shown here in this figure, the refinement normal to the undisturbed free surface can be made by discretizing the free surface in this direction using nearly 10 to 30 cells per wave height. Moreover, the refinement parallel to the undisturbed free surface can be applied by discretizing the free surface in this direction using nearly 80 to 120 cells per wavelength. However, here in this tutorial, in order to reduce the computational cost, we're going to use 10 cells per wave height and 60 cells per wavelength. So to refine the mesh on the free surface, we're gonna apply volumetric mesh refinement on this region. So on the geometry parts, right click on block. On geometries parts, right click on block. Go ahead and select duplicate. Okay, go ahead and rename the block 2 to free surface fine. Let's repeat this process. However, this time rename the block 2 to free surface coarse. For free surface fine, put -10, 0, and -0.6 for the coordinates. Okay, sorry. And also put 18, 10, and 0.6 for the coordinates of corner 2. Okay, now let's define the coordinates for free surface course. Okay, free surface course, put -10, 0 and -1 for the coordinates of corner 1, and for the coordinates of corner 2 put 20, 10 and 1. Okay, so we have defined the coordinates of the volumetric control volumes. Okay, now go ahead and save the simulation. Now under continua mesh 1, right click on volumetric controls, select new. Go ahead and rename the volumetric control 1 to free surface fine. Repeat the process, but this time rename the volumetric control 1 to free surface course. Now click on free surface fine and set the parts to free surface fine. Okay, so now under mesh conditions, okay, click on trimmer. Here check the customize anisotropic size. Under mesh values, click on trimmer anisotropic size, check custom X size, custom Y size and custom Z size. Now expand trimmer anisotropic size, click on relative X size and put it to 10. Click on relative Y size, put it to 10, and click on relative Z size and put it to 5. Okay, we need to do the same for the free surface course. Click on free surface course and set the parts to free surface course. Expand mesh conditions, click on trimmer, check here customize anisotropic size. Under mesh values, click on trimmer anisotropic size, check custom X size, custom Y size and custom Z size. Under trimmer anisotropic size, click on relative X size and let's put it to 20. Relative Y size, put it to 20, and relative Z size, put it to 10. Okay, go ahead and save the simulation. In order to minimize errors in interpolating variables between the two meshes, the background mesh and the overset mesh, okay, we need to use the same order of magnitude of grid density in the overlapping region of the overset and background meshes. To achieve this goal, we're going to set up another volumetric control at the overlapping part of the two regions. Okay, so let's first create a geometry part here. On the geometry parts, here right click on parts, new shape part, block, put here 2, 0 and -4 for the coordinates, and also here put 8, 3 and 4 for the coordinates. Click on create and then close. Go ahead and rename the block 2 to overlap. Now under continue, again mesh 1, right click on volumetric controls and select new. Okay, go ahead and rename the volumetric control 1 to overlap. Now under mesh, now let's first put the parts to overlap here. Okay, now under mesh conditions, click on trimmer. Okay, here check in fact the customize isotropic size. Under mesh values, custom surface size, put 10 here, which is already 10 for relative size of the mesh. Okay, now we need to set up the mesh values for the extruder option. So under regions, background, boundaries, outlet, okay, expand mesh conditions, click on extrusion type, set the type to hyperbolic tangent, now under mesh values, click on extrusion parameters. Here for the direction, put 10, 0, 0. Put 15 here for the number of layers, and also put here 1.4 for stretching. Now go ahead and create a second mesh continuum to be assigned to the overset region. Okay, so for this purpose, right click on continua, new mesh continuum. Okay, we have here created the mesh 2. We're going to assign mesh 2 to the overset region. To do this, under regions, click on overset here, and here set mesh continuum to mesh 2. So right click on models and select meshing models. Here we're going to use surface remesher, trimmer, and also prism layer measure. Okay, so go ahead and close the dialog. Under models, click on trimmer, and here check the do mesh alignment. Okay, under reference values, leave the base size as its default value, set the maximum cell size here to 100. Okay, set the number of prism layer to 2, which is already 2, and here prism layer stretching, set it to 1.1. Click on prism layer thickness and set the size type to absolute. Here set the size to 5 millimeter. Under surface size, set both the minimum surface size and the relative target size to 10. Under template growth rate, set both the default growth rate and the boundary growth rate to slow. Okay, go ahead and save the simulation. Now let's set the mesh size values on the domain boundaries. Go ahead and expand regions. Under overset, boundaries. Okay, click on boundaries. Under boundaries, click on customize prism layer and set it to disable. Under buoy, mesh conditions, click on custom surface size, check the custom surface size here, and under mesh values, put 2.5 for both relative minimum size and relative target size. Finally, under symmetry mesh conditions, click on customize prism layer and set it to disable. Again, here to minimize errors in interpolating variables between the two meshes, we need to use the same order of magnitude of grid density in the overlapping region of the overset and background meshes. To achieve this goal, we're going to set up a volumetric control at the overlapping part of the two regions close to the free surface. Okay, so under geometry, right click on parts, new shape part, and block. Okay, put 3, 0 and -2 for the coordinates of corner 1, and put 7, 2 and 2 for the coordinates of corner 2. Go ahead and click on create and then close. Here rename the block 2 to overlap fine. Okay, now under continua mesh 2, click on volumetric control and select new. Go ahead and rename the volumetric control 1 to overlap free surface. Okay, so click on overlap free surface, set the parts to here to overlap fine. Now under mesh conditions, click on trimmer. Here select the customize anisotropic size. Under mesh values, click on trimmer and check custom X size, custom Y size, and custom Z size. Now under trimmer anisotropic size, put 10 for relative X size, 10 also for relative Y size, and put 5 here for relative Z size. Okay, go ahead and save the simulation. Now we set up the mesh for our simulation. Go ahead and click on generate volume mesh from here. To visualize the mesh, go ahead and right click on scenes, new scene, mesh. Here you can change the orientation. Okay, let's zoom in from here. Here we can clearly see that the mesh has been extruded on the outlet boundary. Now let's create the physics and define the physics that we're gonna use in our simulation. Under continua physics 1, okay, right click on models, select models, implicit unsteady Eulerian multiphase, volume of fluid VOF. The flow is going to be turbulent. We're gonna use the K epsilon turbulence model. Among the optional models, choose the gravity and VOF waves. Click close. You can visualize the model you just selected here. Go ahead and save the simulation. Now we need to create an overset interface between the background and overset regions. Okay, to create the overset interface under regions, multi-select both the background and overset. Right click on one of them and then create interface, overset mesh. The volume type overset interface can be seen under interfaces as overset mesh 1. Here we're going to use a linear interpolation between the background and overset regions. So under overset mesh 1, physics conditions, click on interpolation option and set it to linear here. Go ahead and save the simulation. Now let's define the materials that constitute the Eulerian phases, which are water and air. Under continua, physics 1, models, Eulerian multiphase, right click on the Eulerian phases, select new, go ahead and rename the phase 1 to water. Now under water, right click on models and select models. Here select liquid, constant density, and close the dialog. Okay, we need to repeat the same process to create air. So right click on the Eulerian phases, select new, go ahead and rename phase 1 to air. Now under air, right click on models, select models. Here select gas as material, and here constant density. Go ahead and close the dialog. Okay, so here you can see the models, right? Water and air. Go ahead and save the simulation. Now let's define the VOF waves. So under continua, physics 1, models, VOF waves here, right? Under VOF waves, right click on waves and select new, then fifth order. The fifth order wave model uses the fifth order Stokes theory for modeling the waves, which is more accurate than the first order model. Okay, go ahead and rename the fifth order VOF wave 1 to head waves. In the properties window, put 000 for it's good for water level. Let's put 0 minus 1 for the vertical direction. 0 minus 1. Put 0.5 for wave height here. Put 10 meter for water depth. Go ahead and set the specification type to wavelength here. Okay, so expand head waves here and select wavelengths specification and put it to 6 meter. Go ahead and save the simulation. to set the initial and boundary conditions, we're going to use few functions that are associated with the VOF wave that we just created. Okay, these field functions are generated by VOF wave model based on the wave parameters that we just defined. So under continuous physics 1, initial conditions, okay, click on pressure, set the method to field function, and then set the scalar function to hydrostatic field function, set the scalar function to hydrostatic pressure. Now go ahead and click on velocity, set the method to field function, and then set the vector function to velocity of head waves. So now go ahead and click on volume fraction, set the method to composite. Now under composite, click on water and set the method to field function, okay, and set the scalar function to volume fraction of heavy fluid of head waves. Okay, now click on air, set the method to field function, and set the scalar function to volume fraction of light fluid of head waves. Go ahead and save the simulation. Another important point here is the correct specification of the gravity vector. Here the positive z direction is pointing downward, okay, which is exactly the direction of the gravity vector. Okay, so under continuous physics 1 reference value, click on gravity and set 9.81 for the gravity value. Okay, now let's define the boundary conditions under regions, background, boundaries, inlet, physics conditions. Click on velocity specification and set the method to components. Okay, now under physics values, click on velocity and set the method to field function, and set the vector function to velocity of head waves. Now go ahead and click on volume fraction here. Okay, set the method to composite. Okay, now under composite here, click on water and set the method to field function, and set the scalar function to volume fraction of heavy fluid of head waves. Okay, now let's now click on air. Okay, set the method to field function and set the scalar function to volume fraction of light fluid of head waves. Okay, go ahead and save the simulation. Okay, now under regions, background, boundaries, outlet, physics values. Okay, click on pressure and set the method to field function. Okay, and set the scalar function to hydrostatic pressure. pressure. Okay, now go ahead and click on volume fraction. Okay, set the method to composite. Okay, now under composite, click on water and set the method to field function. Okay, set the scalar function to volume fraction of heavy fluid of head waves. Okay, now click on air, set the method to field function and set the scalar function to volume fraction of light fluid of head wave. Now, to make sure that no wave reflection will occur on the outlet boundary, we're going to set up a damping function close to this boundary over a distance equal to the extruded part, which is 10 meter. The damping function used in a STAR-CCM Plus is a combination of both linear and quadratic damping functions, which are added to the momentum equations as source terms to cancel the vertical velocity component of the flow over a certain distance. Okay, to apply this damping function on the outlet boundary under regions, background, physics conditions. Okay, click on VOF wave zone option and set the VOF wave zone option to damping. Okay, and now under physics values, here under physics values, click on VOF wave damping length and set it to 10 meter. Okay, now under boundaries, outlet, physics conditions, click on VOF wave damping boundary option and set the method to yes. Now we're going to activate the 6th degree of freedom motion solver by creating the relevant DFBI motion object. In this simulation, we are interested in only simulating the vertical motions of the buoy, which is called the heave motions. Okay, so under tools, motions, okay, right click on motions and select new DFBI rotation and translation. Okay, a new DFBI rotation and translation node is added to the motion manager. To assign this motion to the overset region, under regions, okay, under regions, overset, physics values, click on motion specification and set the motion to DFBI rotation and translation. Now let's create a local coordinate system at the center of the buoys. Okay, we're going to use this local coordinate system to define the initial position and orientation of the buoys. So under tools, coordinate systems, laboratory, right click on local coordinate systems, new Cartesian. Okay, set 5 meter for X in the origin, then click create. Okay, close the dialog. Go ahead and rename the Cartesian 1 to buoy coordinate system. You can visualize this local coordinate system in the graphical window, right, by clicking on it, which is obviously here. Okay, here is the local coordinate system. Okay, now let's define the buoy along with its properties. Under DFBI here, right click on 6 DOF bodies, new body, 3D continuum body. Okay, go ahead and rename the body one to buoy. In the properties window, set body surface to buoy. Set the body mass to 780. Under buoy, click on free motion and select Z motion. Okay, since we are only interested in modeling the vertical motions of the buoy. Okay, under initial values, click on angular velocity and set the coordinate system to buoy coordinate system. Okay, repeat the process that we just did here for the angular velocity and assign the buoy coordinate system to center of mass, moment of inertia, orientation, and velocity. Okay, so here also we're going to assign it to buoy coordinate system, moment of mass, buoy coordinate system. You can also check use center of mass, orientation, and also velocity. Okay, go ahead and save the simulation from here. Now let's define the solver settings for the accurate simulation of wave propagation. STAR-CCM Plus recommends using this equation to specify the time step size, wave period divided by the number of cells per wavelength multiplied by 2.4. Here we use the dispersion relation for linear waves to estimate the wave period, which is shown here. Okay, where T indicates the wave period, lambda the wavelength, G gravity, and D the water depth. So by using these equations, the time step size is estimated as 0.013 second. However, note that the estimation of the time step size should also be in such a manner that in each time step the overset mesh moves a distance smaller than the size of the smallest cell in the background mesh. Therefore, considering this point, the time step size that we're going to use here is 0.001. So under solvers, click on implicit unsteady and set the time step size to 0.001, which is already this value. Okay, and set the temporal discretization to second order. Okay, under stopping criteria, set the maximum inner iteration to 5, which is already this value, and the maximum physical time to 20. And check the maximum steps. Now let's create a scalar scene to visualize the motions of the buoy in waves. For this purpose, first we need to create the free surface isosurface. Okay, right click on the derived parts here. Okay, right click on the new isosurface. Select volume fraction of water for the scalar. Here, volume fraction of water. Okay, set the ISO value to 0.5. Set the display to no displayer. Click create and then close. Under drive parts here, go ahead and rename the ISO surface to water surface. Now to set the color of the free surface blue, let's create a custom color map under tools. Click on color map, right click on color map, select new. Okay, here first let's click OK. Okay, and under color maps, right click on user 1 and rename it to water. Click on water, and from the properties window click on color map. Okay, click and drag the blue control point all the way to the other side so that the color bar is totally blue. Okay, set the color space to RGB. Click OK. Now let's create a scalar scene to visualize the free surface. Right click on scenes here, new scene, scalar. Under scalar 1, displayers, click on outline and deactivate outline. Okay, under scalar 1, click on parts and set the part to water surface under the drive parts, and set the function to volume fraction of water. Set clip to off, set outer range to off, set both min and max to 0.5. Now click on color bar, okay, and set the color map to water that we just created. Deactivate shadow, set levels to 2. Okay, deactivate visible. Now click on scalar 1 and set the contour style to a smooth fill. Under expert, here under expert, set the transform to symmetry 1. Go ahead and save the simulation. Okay, now let's add the buoy geometry to the scalar scene that we just created. Okay, so under scalar scene 1, right click on displayers, new displayer, DFBI. Okay, click on DFBI. Under expert, set the transform to symmetry 1. Okay, under DFBI, click on parts, okay, and set the part to buoy. Okay, here go ahead and set the simulation to here. Views, set the orientation to -y and -z. Okay, you can zoom from here and rotate a little bit. Okay, now let's create a scalar scene. Okay, so let's go ahead and create a scalar scene. Okay, right click on scalar 1 and set the color map to water. Okay, under scalar 2, click on outline and deactivate outline. Okay, now click on So now under tools, annotations, drag and drop the solution time into the graphical window. Let's put the solution time here. In the properties window, activate background. Okay, set the font to Times New Roman bold here. Now let's right click on it and edit the annotation here. Set the width stretch factor to 0.6 and set the height to 0.04. Okay, go ahead and save the simulation. Okay, you can export the scalar scene for later creating animation from the exported images. So for this purpose, under attributes, click on background, set the color here to solid. Okay, click on update, check save to file, output directory here, click on it, and here you can create a new a new file and rename it to Buoy motions. Okay, so click on Buoy motions and now click OK. Put here trigger to timestep. Under update, click on timestep frequency and set it to 20. Click on hard copy and set the resolution to 800 and 600. Here under annotation, click on logo and deactivate visible. Now let's create another scalar scene to visualize the movements of the overset mesh. Okay, right click on scenes, new scene, scalar. Now right click on drive parts, new part, section, plane. Okay, set the origin to 0.001 and also 0 for Z, and set the normal to 0, 1, 0. Okay, set the display to no displayer, click on create and then close. Okay, now under scalar 1, under scalar 2, displayers. Okay, click on outline and outline 1, deactivate outline. Click on scalar 1 here. Okay, and set the contour style to smooth field. Okay, under scalar 1, click on parts and set the parts to plane section under drive parts. Change the orientation from here to minus Y and minus Z. Okay, click on scalar field and set the function to volume fraction of water. Okay, click on color bar and set the font to Times New Roman bold. Okay, activate background here. You can also zoom from here a little bit. Okay, now right click on displayers. Here, new displayer, geometry. Click on geometry and deactivate outline. Okay, and activate surface. Under geometry 1 here, click on parts and set the parts to buoy. Click on geometry, under expert here, set the transform to symmetry 1. Okay, so you can change a little bit the orientation here. Set the color mode here to constant. Color mode here to constant. Okay, under geometry 1, click on color and set it to cyan. Okay, so now under tools, annotation, drag and drop the solution time into the graphical window, put it here, right click on it, and now set the width stretch factor to 0.6 and set the height to 0.04. Now go ahead and save the simulation. Okay. In this case, again, you can export the scalar scene for later creating animation from the exported images. Okay, for this purpose, under attributes, click on updates here. Click on update, check save to file, output directory here, and create a new files and rename it to mesh motions. Okay, select the mesh motion, click OK. Here put the trigger to time step. Okay, and under update, click on time step frequency and set the frequency to 20. Click on hard copy and set the hard copy resolution to 800 and here to 600. Now let's create a report to monitor the vertical motions of the buoy. So right click on reports, a new report, 6 degree of body acceleration, and here you can choose the 6 degree of 6 DOF body translation. Go ahead and rename the 6 DOF body translation 1 to heave motion. Okay, click on heave motion and in the properties window set the direction to 0, 0, 1. Okay, now right click on heave motion and select create monitor and plot from report. Okay, note that you can use the same process here to create reports to monitor the forces and moments acting on the buoy. However, this is beyond the scope of the present tutorial. Okay, go ahead and save the simulation. Note that you can also export the heave plot monitors for later creating a dynamic plot monitor from the exported images. Okay, for this purpose, right click on the monitor plot of the heave and of the heave motion here, and select edit. Okay, here you can edit the font of the titles of the axis also. Okay, I'm not going to enter into detail about this. To export images, under update here, click here, check the save to file, output, click on output directory here. You can create here a new file and rename it to heave plot. Okay, go ahead and click on heave plot and click OK. Set trigger here again to time step. Under time step frequency, set the frequency to 20. Okay, and also here you can set the hard copy resolution, okay, to the same as before. However, you can also set the aspect ratio here to 16:9. Go ahead and click close. Save the simulation from here. Before running the simulation, let's first initialize the simulation from here to see if everything is working well. Okay, you can change the wave propagation direction to be from left to right. Okay, it is very simple. Let's first do for this scene here. Okay, you can do this from here, right? The orientation you can change. Okay, and this is it. Go ahead and save the simulation. The same we can do also for this one. Can zoom in further to better see the movements of the mesh. However, here we have to do something else here for scalar scene 2. Under scalar scene 2, displayers. Okay, click on scalar 1 here and display mesh. Okay, go ahead and save the simulation. Now that the simulation setup is complete, go ahead and run the simulation from here. At the end, we have the post-processing step. It is worth mentioning that the computations are performed on a desktop computer consisting of 64-bit Intel processors i9 with the velocity of 6.6 GHz and 64 GB of RAM. The simulation takes almost 4 days to finish. Here we can see the free surface waves. Okay, here we have the residuals. Note that to better understand the behavior of the residuals, I have set the normalization options of the variables under monitors to off. Here we can see that I have turned it to off, normalization option for all of the variables. Okay, here we can also observe the behavior of the buoy heave motion, right? Which, as we expected, is oscillating due to the presence of waves. Here we can see the volume fraction of water and close to the outlet boundary here. Okay, we can observe that the wave elevation goes to 0 because of the extruded mesh together with the damping function that we applied to the region close to the outlet boundary, right? This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos please subscribe to this channel.